exhaustive grid option in the layout step. Jeffrey, for some highly infrequent events, such as, for example, co-labeling of BRDU and, let's say, NUN, for these types of events, it may be impractical to do a systematic and random image stack acquisition within one contour. Now, even if you are using serial sections that don't come one after the other, let's say that you were using tissue where your serial sections were every 6 sections, you may want to exhaustively sample all of the BRDU stained cells in each of your sections. This essentially means that you want to count all of the BRDU positive labeled cells in this one region of interest. To that end, the exhaustive grid option makes it such that the entire area of your entire contour region of interest is imaged. In the end, when you do your analyses, you will be counting all of the low-frequency events in each of your sections. So whereas it sounds like you may not be doing actual data estimation because you're counting every object, it's important to remember that you're counting every object on only those tissue sections which you are sampling. Sinan has a question about hardware, specifically the type of hard drives that should be used. We recommend that for the acquisition process, you write directly to an external hard drive. We've had some users write their data to either networked drives or external USB drives. What we've encountered is that there is a potential for data buffer interrupts, or there may be some problem in writing to an external hard drive. This may result in some technical problems. Our recommendation is to always acquire your tissue and write the files directly to a local internal hard drive. Great. Thank you all for your questions. Let's move on now to our final submenu, which is the Acquire submenu. In the Acquire submenu, users will be prompted to specify pre-focusing locations, pre-focus to the top of tissue sections, save imaging configurations for future use, and also optimize camera settings for multi-channel fluorescent acquisitions. I will now go on to the next step, or step 10. In order to obtain SRS image stacks of your tissue from the top to the bottom of the Z position, it is important to indicate to the software the location in space of the top of your tissue. We recommend measuring at every acquisition site. In this way, you will have the most information about tissue top locations and have a greater chance of scanning and acquiring Z-stack images from the entirety of the Z-axis. Alternatively, interactive site selection is possible. In interactive site selection, the user selects locations upon which to go through and measure tissue tops. By hitting the top of section button, the software will then take me to these locations where I will focus at the top of the tissue. A third option is to simply set the current Z position as the top of the tissue section. Using this option means that regardless of the true top Z position of your tissue, SRS image stack acquisition will always begin at whatever the Z position is now. I'm going to select to identify the section top at every site. stack acquisition in the future by simply loading the grid size, counting frame, and various other values for future use. I will demonstrate how to save this. There, we have successfully saved these settings. The next time that I need to acquire image stacks from another subject of this group, whether it be control or experimental, I can simply use these settings by loading them up, as you saw in step 1. Step 12 is the final step, and it's also known as the image acquire step. The acquisition list selects all of the regions or contours which you have delineated that are going to have image stacks sampled from them. As we have only delineated one contour, only one contour is listed and selected. Multiple contours would be listed here. The acquisition box allows the user to insert a delay time before acquiring each image. While we will not use this today, some users may find it helpful to have a delay between each image. One potential reason for having such is that stage movements may not become dampened before the next image is acquired. This may lead to blurry or out of focus images. If users find that this is the case, adding a delay time in between the acquisition of each image may solve the problem. As we are performing a multi-channel acquisition, I will select the multi-channel acquire box. I will then select multi-channel setup and pick the channels that I want to acquire. In the acquire setup box, I can define whether I would like red, green, and blue channels acquired, or any combination thereof. This tissue has both GFP and DAPI stain, and thus we will pick those two. Now, we must optimize our camera settings for each channel. To do that, we will use the multi-channel control, the camera settings box, as well as a video histogram. Our goal will be to use the exposure to achieve as broad a histogram as possible. I'll begin with the DAPI channel. First, I select DAPI under multi-channel control. I'm going to use my macro view to move to a representative location of tissue. I will then focus down. You will notice that as I move the exposure settings, the shape of the histogram changes. Optimal images will be achieved when the histogram is at its broadest along the x-axis. It's possible for users to adjust the black and white points as well as the gamma shift for this acquisition. The default button will bring to its default values and optimize, direct the software to pick what it believes to be an optimal value for black, white, and gamma. Moving to GFP will cause the software to save these settings. I will now switch to optimizing the GFP channel in the multi-channel control box. I will pick a lower exposure time and try to get as best a histogram as possible. Satisfied that I have the optimal exposure and histogram settings, I want to close my expectation shutter once again to avoid deletion. I would like to demonstrate that if I move from one channel to another, that the settings that we have predetermined for both exposure and histogram remain saved. Now ready to begin our acquisition. At this point, it would be useful to make sure that you are in no position to shake or move the table or platform which supports your microscope. To begin the acquisition, simply press click to start acquiring. The software will now direct motorized hardware to engage the appropriate filters, the appropriate camera settings, and acquire the images in Z at each of your locations. As you can see from the bottom of the screen here, we are going to be acquiring at 4 locations. I'd now like you to post your questions regarding save your imaging settings or feature acquisitions, selecting image file types and file output locations, or questions related to setting up your camera optimization steps. Please post them now. So a number of users are asking why we recommend JPEG 2000 versus TIFF. Our engineers have been working towards improving our ability to handle specific image data files. We found that using JPEG 2000 results in very high-quality images that are an order of magnitude smaller in size than conventional JPEG images. Also, our software works with JPEG images in such a way such that you will always retain your original data. Making modifications to things like brightness, contrast, or saturation levels will not actually change or modify the original data. In this way, it is always possible to go back to your original data that you have captured and look at it once again fresh. There's a question regarding acquiring multiple channel images without a motorized filter on the microscope. For those users that don't have a fully motorized microscopy system, our software is designed to work with this situation. So what we do is we set up a series of device command sequences which simply prompt the user to engage the correct filter. So whereas the system I'm using now simply drives the microscope to make the movements and filter changes, what you would experience is a message telling you, now please move to this filter, or now please move to this other filter. Essentially, it can still be done, except it's done in a much more manual fashion. Great, thank you for your questions. Well, as we can see here, our acquisition is now done. I want to go ahead and close my expectation shutter once again. And now I will look at the acquired results. The acquired results box indicates to me that the acquired process has been completed. It tells me that all of my runs were completed, none were canceled, and none failed. I now want to go ahead and press I'm done. The software asks you if you're sure if you wish to close the workflow, which you can do knowing that your images and data files have already been saved. What you have just observed is a step-by-step live demonstration of the use of an SRS Image Stack Series Acquire workflow. We believe that SRS Image Stack Series are a useful method for analyzing multi-channel stained tissue offline. This methodology has many benefits, including a more efficient use of microscopy hardware, avoiding a bleaching effect while analyzing your tissue, acting as a digital archive of your analysis, as well as being very easy to use. I'd now like to open up the questions for any final questions. Any questions that we do not answer today, or which you perhaps do not think of today, can be forwarded to us by either emailing us at info@mbfbioscience.com or by visiting our forum at forums.mbfbioscience.com. Hi, Genevieve. You were asking if we can demonstrate how to open our image stacks, or how you open these our image stacks. These image stacks are acquired as a series of JPEGs or TIFFs and a DAT file. The DAT file contains information regarding the contour that you've generated and the location of the C stacks in that contour. The series of image stacks that you generated can be opened by either directly opening the DAT file in which case Stereo Investigator will automatically load the Z-stacks at their correct position relative to the consort. Or you can open the data file using our optical fractionator workflow. This topic of how to work with these files in one of these other workflows is a webinar all in and of itself. Kate has a very good question. She asks, does the software acquire images using one filter and then the other, or does it switch back and forth between filters in each section? Kate, the answer to that is that it can do both, and it's up to the user to decide which of those two options they would prefer. Dana asks, what is the best way to transfer acquired data to a different workstation? Well, Dana, as we've already mentioned, we don't recommend you saving the acquisition directly to an external or network drive. But once these image files are saved onto your local hard drive, you simply move the data file, the DAT file, and all the image files together to your workstation computer. There, you will open your DAT file, and the software will either prompt you to point out the folder where the images are at, or it's possible that your software and your DAT file and your images are in the same folder, in which case the program will find them there. Carlos asks a good question. Does the DAT file contain enough information that you would not need to define a LAN on an offline system? Actually, Carlos, the information regarding the lens is on a separate file, is a lens file, and we would recommend using the same lens information on a different workstation. So you would have to use a workstation that has the same lens file. Thank you very much for all of your questions and for your patience and your attention. We'd like to thank you for joining us for our latest installment of our web-based live demonstrations. My name is Jose Maldonado, and it's been a pleasure to help you. Have a good afternoon. Good morning. My name is Jose Maldonado, and with me today is Dr. Susan Hendricks.
Hi, everyone.
Welcome to the latest installment of our continuing series of online courses. Today we will be presenting conformal stereology, a technical innovation from MVF Bioscience and Carl Zeiss Microscopy. Before we continue, please take a moment to adjust your speaker volume so that you may listen to us at a comfortable level. We'll pause for a second to allow all of you time to do that. So, the very first question that we want to address here is, why would I want to perform conformal stereology? The answer is simple. If you want to quantify spines, synapses, co-labeled cells, or other very small things such as fibers, you're going to want to have true systematic random sampling. You're going to want to have conformal X, Y, and Z stacks. You want to be able to rapidly delineate your region of interest at a low magnification to avoid photo fatigue. And you really want the ability to automatically capture and place multiple conformal Z stacks at the correct X, Y, and Z positions relative to each other at high magnification within a single data file. Stereo Investigator, along with Zen software from Zeiss, work together for the efficient acquisition of conformal systematic random sampling image sites. A typical LSM stereology system configuration consists of the Zeiss 5 or 7 series laser scanning microscope running Zeiss Zen version 2009 or later. Additional components required are a motorized stage, a focus encoder, a digital camera with appropriate light source, as well as stage controller hardware. You'll also need a PC running Zeiss Zen 2009 or later, plus Stereo Investigator version 10.2 or later. In this webinar, you can expect to see a short introduction to stereology, conformal microscopy, and an explanation as to why the two are a natural fit. A step-by-step demonstration of Stereo Investigator along with Zeiss Zen for the acquisition and analysis of conformal systematic random sample image stacks. We will also have question periods throughout to allow you to submit your questions via the question window.
Any questions that are not addressed by the time that we finish this webinar will be sent via email to each participant.
So, in order to get started, why don't you take us through a brief description of what stereology is?
Sure, I'd be happy to. So stereology is an efficient means of quantification. It allows you to move from the qualitative qualitative differences that you may see to quantitative, statistically valid comparisons. It is considered the gold standard for reporting counts. Profile counting can be biased, and density measurements, the number of objects per unit volume, may not reflect the whole region or indicate a change in number. Stereology can be used to quantify a number of biological features, including cell population, cell size, regional volume, area fraction, or fiber length. The most commonly used stereological probes are listed on the right, and those are integrated into Stereo Investigator. We're going to focus on the optical fractionator probe, which allows you to quantify numbers of objects, so cell populations, synaptic numbers, spine numbers. In fact, Daniel Peterson pioneered the use of confocal stereology for quantifying objects using a confocal laser scanning microscope back in the 90s. And we've worked with him and since that time to continually improve the process to make it more and more integrated and intuitive. One of the hallmarks of stereology is systematic random sampling. What I mean by this is that we achieve systematic sampling to enhance efficiency by keeping the grid spacing and the counting frame size the same throughout all your sections through your region of interest. We don't want to count everything that's possible within your region of interest. We want to sample and only count a subset of the available synapses in the entire striatum, for example. It's randomized because the location of the grid and therefore the counting frame always starts at a random location. This is done by Stereo Investigator. And so to illustrate that process, if we were trying to calculate synapse number in the striatum, we would delineate the striatum, define our grid size and our counting frame size, and Stereo Investigator would systematically fill that grid with a random offset over the region of interest. With each successive row of the grid, you can see that while the size and the spacing of the grid and the counting frame remain the same, the number of counting frames that overlie your region of interest and their placement is going to be randomized each time. Stereology also requires a thin depth of field. An important aspect of stereology is the ability to be able to discriminate whether or not an object interacts with your stereological probe. And so we need high resolution and a thin depth of field in order to be able to discriminate objects that are close to each other in X, Y, and Z positions. When you are performing stereology with bright field or wide field structured illumination applications, these thin depths of field are provided mainly by the objective lens, the numerical aperture of the objective lens. For bright field applications, it's also impacted by the condenser that's used. When you're looking for something that's very small, however, you want to be able to have greater resolution than can be provided by the objective alone.
That's right, Sue. And in situations where users try to perform stereology using wide field fluorescence, this can really become evident. Now, we've worked with guys in the past to provide integration with various types of their hardware. And we found that our users require more and more precision in X, Y, and Z to be able to identify their objects of interest. To this end, we also integrated the use of structural illumination devices, such as the Apotome 1 and 2. The Apotome operates by removing out-of-focus light through an algorithmic process and the application of shadows onto your tissue. The differences can be quite remarkable. You can see here that a wide field image incorporates a lot of light that is above and below the focal plane of your region of interest, whereas a structured illumination device looks at images that are much sharper in X, Y, and Z, and allows the user to define objects of interest much more clearly. In regions of anatomy where cells are very densely packed, you can see the difference right away.